Hello, and welcome to this Leetcode problem number 315, count of smaller numbers after self. Right, so this is a Leetcode hard problem, and unlike a lot of the other Leetcode hard problems we see, this problem is actually a relatively hard problem. I mean, it's a unique problem in the sense that you should know how to solve it. There's an insight, a key insight which you can solve it, which is a little bit non-trivial. But after you have that insight, this problem becomes an easy to medium level question, or sometimes actually an easy level question. So this problem is about insight, and so this is going to be a little bit of a longer video. And I'm going to talk to you not about solving this kind of problem, but solving any kind of problem with with this category. So let's get started. Right, so let's read the problem statement. It's count of smaller numbers after self. Right, so you are given an array nums, you have to return new counts array. So you're given an array, you're supposed to return an array. The counts array has the property where counts I is the number of smaller elements to the right of nums I. Right, so for every number here, let's have for every, let's say for 5, we have for 5, what are the numbers this, like on the right of it, which are smaller than 5. So 2 is one such number and 1 in such numbers. So in all there are two such numbers which are smaller, so the answer here is 2. How many numbers of right of 2 are smaller than 2? So there is one such number, which is this one, right? So there is 1. How many numbers smaller to the right of 6, which is smaller than 1, smaller than 6? It's actually 1. Right, how many numbers right to the 1? There are no numbers right to 1 which is smaller than it, so it's 0. Right, so 2110 is the answer to this question. Right, so the constraint here is we are given a array of length 10 to the power 5. So it's like pretty big array, and out of that that big array, what we need to do is we need to find out generate this count array which is of the same size of the number actually does not matter here, so it just says that it will be an int. That is not a problem, but the problem is the size of this array. Right, so what is the naive way of solving this problem? The naive way, or the simple way of solving this problem, would be to actually, so this problem looks very simple to solve. So what's the hard part about it? You can look at the number from the right, traverse them, and count the number which are which is smaller than that. Right, and once you do that, you can do it for the other number, for the other number, for the other number, for the other number, right, and so on and so forth. You just need to do that. So let's see what's the complexity for that. So for the first number, what you observe is that, let's say it's the, you need to check for like n numbers, n minus, if the array is of length n, you need to check for n minus 1 elements to the right of it and see. So if this 5, then there are like n minus 1 elements on the right of 5 which you need to check. Then you have to check n minus 2 elements after that, n minus 3 elements after that, so on and so forth. For the second last number, which is in the right of it, you just need to check the number to the right of it, and the last number you don't need to check anything to the right of, because there is nothing to the right of it. So overall the complexity, so this is actually n minus 1 into n plus 2, so on and so forth, adding up to 1. So if you remember the formula of this is n into n plus 1 by 2. So basically, like, it will be like n minus 1 times n divided by 2. Right, so this is nothing but, if you don't remember the formula, it's okay, because this is quadratic complexity. Right, it's O of n square. Right, and O of n squares for input length 10 to the power 5 is actually too much, and we are not, O of n square is actually not the right approach for doing this. The question one asks is, for such a long input length, can you have a shorter or a faster algorithm? Right, and the answer to this question is actually yes. You can actually get faster than O of n square in this question. So how, one might ask? So the answer to that question is that you need to just look at this question for a while, and if you look at this input, what are we trying to do? We are trying to actually, where do you actually need these comparisons? You need these comparisons when you sort any number, right? So when you're sorting, so for any stable algorithm, let's say merge sort, or any stable algorithm which is a stable sort, which means that the relative ordering of the elements don't change if the both of them are same. You can look up sort, what is stable sort. But for any sorting algorithm, what is the key insight is, the insight is we need to count the numbers which move to the left of a given number while Sorting, right? So when you are sorting this array, the numbers which we just have to take care of, the numbers which move to the count, the numbers which move to the left of 5. So numbers 2 and 1 will move to the left of 5. So we saw that there are two numbers which are moving to the left of 5, so we keep a count of them. There will be just one number moving to the left of 1, left of 2, so that is why the answer is 1, right? So the key inside is we need to count the numbers which move to the left of the given number while sorting, right? And if you are able to count this in an efficient manner, if you are able to count this in an efficient manner, then we have sorting algorithms which can sort in log n, like n log n. And if you are able to do that, then if you are able to count this while sorting, if you are able to count this in less than n log n, or like n, or like whatever in less than log n at max, then you can guarantee that the complexity or less, so n log n or less, if you are able to count. So n log n is the sorting overhead, n log n or less would be what you use to count the numbers of pair which go from left to right, from right to left. So then you can say that the entire complexity of the answer of this question can be reduced to n log n. And once this becomes n log n, we have actually got better to n log, from n square to n log n, which is actually good enough for these constraints, right? So the idea is, for which algorithm are we able to do that? And the answer to that question is actually merge sort, right? So do you remember merge sort? Let's actually recollect the merge sort algorithm. Uh, so let's go to the drawing board and talk about merge sort. So while merge sort, what did we do? We had what we had was, we had this array. We broke the array into two parts, like we halved the array, and then we halved until there are only uh, single elements left, and then we did the merge step, right? Let's do that. Let's do the merge step. So the array we talking about is like 5, 2, 6, 1, right? Now 5, 2, 6, 1. So you could separate them as 5, you could separate them as 2, you could separate this as 6, you could break them as 1. This now becomes 5, this now becomes 2, this now becomes 6, this now becomes 1, right? Now the second step is actually to merge these arrays, right? When you're doing merge sort, if you recollect merge sort, you merge two of them, then you merge those two into bigger ones, and you do it until you get back the size of the array, right? Now while merging, what we can do is, we can be smart, we can literally keep track of, let's say we keep track of the so 5, 2, 6. I'm actually sorry with the handwriting, because I hold the mouse in the right hand like everybody else does, and I'm a left-handed person, right? So the world was actually made for the left-handed people, was made for the right-handed people, and we left-handed people actually have troubles using things made for lefties. So this is 5, 2, 6, 1. So all of them. Let's see how many swaps are we making, right? So when you're comparing them while merging them, what you do is, you have two pointers, one pointer here, one pointer here, and you see which one of them is smaller. So 2 and 5. So 2 is smaller. So 2 comes here and 5 comes here, right? Let me change the color to blue. So 2 comes here and 5 comes here, right? Because 2 is smaller and 5 is small. So whatever is smaller you write first, then you increment this pointer, but this is out of bounds. So you have this, and you use this right now. Now you realize that 2 actually went to the left of 5 during this pass. So 2 went to the left of 5. So 5, you increment 1 by 5 in this pass. In the similar level, 1 will go to the left of 6. So 1 and 6 would be how this will be sorted, right? 1 will be going from the left to 6. So 6 will be incremented by 1, because there is one element which went from the left to 6. Both of them, there is no element which went to the left of it, so 0, 0. Right. Now when we are actually working with this array 2, 5, 1, 6, you have a pointer here, you have a pointer here. Now when you have a pointer here, you first say which of them is actually bigger, 1 or 2. So 1 is actually bigger. So you can write 1 here, right? Now whatever will come after 1 now will be basically 1 is before everything else, right? So in all of these things where 1 is before, you have to add 1, right? So other than 1, all of them, then you just add 1, right? So 1 is before 5, 1 is before 2, right? Now so like in this side of it, right? So one is before 5, one is before 2 in this side. Now when you are looking at now this pointer increments to 6. Now you are comparing which one is bigger, is 6 is bigger or 2 is bigger. So it's like 6 is bigger, so we will have to add 2 here, right? Now when we are adding 2 here, what will happen is that there is the 2 does not swap from anything, it does not come from one side to the other side, so there is like nothing added anywhere, right? Now we also make sure that the pointer here, since we change to the pointer moves to the left, which one is bigger, 5 or 6? Exit 5 or 6, 5 here, and this pointer now shifts, but it's out of bounds, so you just remain with 6. In none of these operations we had to in none of these operations we had to use we had to change the relative order of these things. So there is no other change that happens, so it's 0 0, right? So totally, if you take the total of this, you have 2 1 1 0, right? Which is the exact array we wanted, right? Which is the exact array we wanted. So this is the output of this. While you got a sorted array, you don't care about the sorted array, but you need this as the output. Now you realize that uh, to get this as the output, we need to find an efficient way to generate. So first of all, what is the length of this? So the length, how deep would be this would be log n layers deep, right? Because the number of such levels are equal to the levels of merge sort. So how many levels? The merge sort is log n levels deep, right? Log n levels deep. So this would be log levels deep. So if you're able to generate this with complexity of order of n on every level, then we can say that the entire counting and the addition can happen in n log n, right? So if we are able to guarantee calculation and addition in n log n, because these will be n elements, and if we are able to generate these rows with like in order of n times, then we are actually done. If we get this in n log n, then like the sorting is O of n log n plus n log n, the complexity totally will become n log n, right? So now the question reduces to, like, the question reduces to the fact that we have two sorted arrays like 2 and 5, 2 and 5. How do we count the elements which move from the left to right in the sorted array without, like, in O of n time? So if we are able to given a sorted array at any stage of this merge sort, if you are given a sorted array here and if we are given a sorted array here, we have to count the number of elements which went from here to here in O of n time. If we're able to do that, we'll be able, like, if we have to make this, and this is nothing but the count. So we just have to have an algorithm to count elements which went from left, like from the right to the left, in order of n times for any intermediate level. If you could do it for any intermediate level, it generalizes, and then for there log n level, so n into log n would be the complexity, right? So this is where we just think a while, how do we do that, and once we're able to do it, we'll just program it along with merge sort, right? So yes, so let's see. So for example, we have two arrays. We the first sorted array on this side we have would be 1 4 6 4 6 7. Let's say, for example, this is the sorted array. We are in some position of merge sort, and we are sorting this array, and we on the other side we will have 2 3 5 and 8, right? So this is the sorted position. Now you need to compute the elements which go from left, like from the right to the left, right? So how are we going to do that? So let's see. We make a sorting algorithm which with in O of n generate that count array, right? So we start with text box. Here's the array elements, right? So 1 4 6 7 2 3 4 8. So for like 2 3 5 8, see, these are sorted. Now you need to just keep track of them. So how do we keep a track of them? We'll actually make a sort of a chart for them, which will, you know 2 3 4 5 6 7 and 8. So we might discard what we don't need, but essentially this is the, this be 1 2 3 4. So tracking all of them, right? 5, 6, 7, and 8, right? We might just need one box, but yeah. So we have two pointers here. So this is the start pointer. So this is the left pointers. Like in merge sort, we have the left pointer. We have the right pointer, right, which is the right pointer, and then we have the mid pointer, the mid M, right? So L, R, and mid. So what we do is we start with two different iterator pointers. So these were like pointers for pointing the merge sort. Then the iterator pointers. There is this iterator pointer called I, and then there is this other iterator pointer called J. Right. So these iterator pointers, I think the gray will not be visible as much as I thought it would be. So the iterator pointer I starts from here. So this is where I starts from. I. And J starts from where M starts from. So I starts from where L starts from, J starts from where M starts from, right? And then what we try to do is we try to compare the element of 1 and 2. So let's say we are comparing element of like 1 and 2. Which one of them is bigger? So we try to increment J until we get so let's compare, like and so 1 and 2. So which one of them is bigger? If 2 is bigger, now if 2 is bigger, it means the element of the right side is actually bigger, so nothing is gonna get swapped here, right? So once this happened, whatever element corresponding to 1, it is a 0, nothing gets swapped because like it's already on the right. Then we actually increment our I pointer and make it point to 4, right? Okay, so now the J pointer points to 2. So 2, if the J pointer is pointing to 2, is there anything, so which one of them is bigger? Actually 4 is bigger. So yeah, you are like, okay, 4 is bigger, so the J pointer will increment, the J pointer will become 3, right? So which one of them is now bigger? 3 is like bigger, so J pointer will once again increment, right? So the J pointer will now become 5. Now which one of them is actually bigger, 4 or 5? So 5 is bigger, so this time this is bigger. So the difference between J and mid, so this difference, so how many elements had we traversed to the right? So these are the elements which will be transferred from this side to this side. So how many elements? 2 elements. So for 4 it is actually 2 elements, right? For 4 it is 2 elements, right? Which tell you. Now for 6 we are sure all the elements which transferred for 4 are automatically going to get transferred for 6. So 6, there is already 2 elements which we get from 4, right? So that's not a problem, but there can be more elements as well. So compare I from the I increments to 6. So compare I is equal to 6 to 7 to 5. Which one is the most bigger? Actually 6 is bigger, so J still increments to 8. Now as J increments to 8, now which one of them is bigger? Actually 8 is bigger. So all these elements, so there was 2 of 5, and this is already due to 4, and then this was 5. So this 2, instead of 2 we have 3, right? Because they already had, so we did not have to reinitialize J. If we had to reinitialize J and reiterate the elements, then it was n square, but we just increment J all the time. And once we increment J, so I is incremented from 0 to mid, like 0 to M, and J is incremented from mid to R. Now when J is reached R, we just say I is incremented to 7. Which one of them is bigger? Actually, so 7 is bigger, so 7 is smaller. So all these, so the difference from I2 is 3. So 3, so whatever elements that transfer from left of 6, there will be automatically be transferred from to the left of 7. So automatically 3, there is no new element added because of 7, and 8 is bigger, and so nothing will be transferred. So for A, so this is how you generated the the transfer numbers for this array, right? And so this is in single pass you will be able to. So when you will ask what about these numbers, so this is an intermediate step. In steps before and after this, these numbers will also be included, the numbers left to these numbers will also be counted. But did you get it? You traversed the array. So I traversed from L to M, and from J traversed from M to R. They traverse from M to R. So all in all, we have two pointers, one traveling this half, one traveling this half, and both of these pointers we ended up just traveling the array once. So the complexity of this is O of n. We are able to generate a map with O of n. We are able to keep a track of what went left and what went right with O of n. And once we're able to do that, then the algorithm is solved, the problem is solved. We could keep track of all of them, and then we could add it at the end of the day, and that will be the answer to this question. So the key part is to actually see this intermediate level, and if you have, so this method can be generalized for any intermediate layer, and we'll recursively do it, and the answer is there, right? So hopefully this is clear. Let's now code this question, right? So this is clear. So let's now code the question. So now when you're coding this question actually uses like merge sort. So for merge sort, if you know the algorithm of merge sort, there is a splitting step and then there is a merging, like there is a splitting step and there is a merging step, right? For merging step, what we are going to do is we are going to use an inbuilt function of C++, which is std in place merge. So let's write this function down, std in place merge. Now what does this in place merge do? It takes in the start index, so array dot list or like array dot start. It takes in dot begin. It takes in the array dot mid, or like if there is nothing like array dot mid but array dot end. It takes in the mid, like array to mid and from mid to end, and both of those it contiguously merges them, like O of n, the merge sort, it actually merges them automatically. So do you understand? This is the merge step. So you could actually implement merge step, merge sort the way we want to implement it, but C++ gives us this in place merge function which actually does that merging step for us, right? So just when you know the programming language well, when you actually understand that, so you can really score well, you can really get these questions correct, right? So we could write this in place merge function. It was nothing but the merge function which I described earlier, but C++ already has this in place merge function. So what we need to now do is use this in place merge function and just implement the counting logic. Once you are able to implement the counting logic, any of this question can be very easily solved, right? So now there is also an other important catch, which is that this takes in iterators, right? This is an iterator, this is an iterator. So if you study STL of C++, there is a very important notion of iterators. So instead of solving this problem by passing the entire array, and like if you pass the entire array, the time complex, the problem will actually time out, and because there are like big arrays to pass, instead of that we are actually passing just all the arrays by reference. So we are going to use the iterators. Hopefully everybody is familiar with iterators. If you have a vector int of nums, then the array pointing to, like the pointer pointing to that vector, the iterator pointing to that vector is nothing but vector of, if you know, so vector comes from the standard namespace, the standard vector int and the iterator, right? So if you do, so for example, for auto like num in nums, so this num variable is nothing but it's an iterator throughout these nums. So it's actually, this is what auto actually fills inside instead of you know so this is the iterator, and that is what the auto fills inside v, right? So this is why actually very long. So C++, 11 and C++ 14, all of them actually support this auto keyword. Before that we had to write these iterators. So in this problem typically we'll have to write these iterators, because we are going to pass this to a function called merge, count merge, which is going to take in an iterator, right? So in this question what we need to do is we need to first make a temporary vector, a vector of vector, sorry for the spelling errors, int, a vector of int, let's call it temp. So what this does is this takes in the index. So you have the count index actually have to return according to the initial configuration. So the count of the 5 would be according to where the position of 5 was. So when we'll spot them, we'll actually scramble the position. So to remember where this 5 already was, we have to use like we have to actually keep track of, we have to store them with also with the value and also the index, so that when we have to update count, we know where to update count, right? So vector of int of temp. So what does this vector of int of temp does is, so for int I is equal to 0, I greater than temp dot not temp, nums dot size I plus plus. So for all numbers in num array, right, for in this vector, what you do is you just do temp dot push back another vector. What does it that vector is? The vector is it's now like nums of I, comma the position I, right? So we will be operating on the zeroth element of this thing, but then we'll also keep a track of the first element of this thing, right? So push nums of I. We'll also have to make a count array and also have to pass the count array by reference, right? So we could pass it by reference, we could also pass it by value, whatever the way, like you could, arrays are always passed by reference, but instead of passing the entire array, you could just pass the iterator. So instead of passing the iterator, we could just find the pass the pointer to the first element. You can see that. So let's make this array count. So the array count would be nothing but vector int count of 0 comma nums dot size, right? It's the same size as num, and initially there is no count, so initially we initialize them to 0, right? Then we call this function merge count, or whatever you want to call it, merge count. And this function merge count takes in uh, temp dot begin and temp dot end, and also the array count, and it actually changes the value of this array count, and we are able to, like, not the changes the value of this vector count, and we are able to return count as the changed number, right? So this is what we want. Now what is this temp dot begin, what is this temp dot end? These are vectors, so let me show you what they are. So the new element would be vector. So what this function returns a vector of this actually is a void function, right? Because it doesn't return anything. It's a void function because it operates directly on count. So it's a void function called merge count. What it takes in is a temp begin. So what was temp? Temp is a vector of vector. So it will take a vector of int and its iterator iter iterator, right? But this is and we could name it whatever we want to. We could name it like the left side, the right side, but instead of just doing this, we could also do the easy way. Define vv iter as this thing. So the next time so this is just vv iter, right? L, it's vv iter, right? And vector int, and because it's of course a pointer to the vector int count. Okay, so this is actually where we are going to implement our merge sort. The first thing we need to do is we need to define this element m. So m is nothing but the midpoint of the merge sort, so you always have to compute the midpoint. So midpoint is L plus L first, okay, L minus R of divided by 2. It might so happen that there before existing a midpoint will actually at the end of the array. So we have to first write the terminating condition. If R minus L is greater, this is smaller than equal to 1, then you simply return. You simply return, because this is like you will not be able to compute the mid. But if this is not the case, then mid is actually computable, and this is the mid, and you just say like, because it's merge sort, you just say it's merge count of lm count, and from left to right, and then it's merge count mr count, right? So this is lm count, mr count, right? So easy. So now we need to, once this happens, the end to end of this would be in place I like it's std is actually using namespace std. You don't need to use it, but I like to use it. If you do like game programming or hardcore C++ programming, it is very important for you to actually not use namespace and write these things, so you understand from which namespace this comes from. But in general, in computer reporting, it's okay, right? Standard cider in place merge in place merge of what do we want? We want start begin like L M R, right? So the in place merge of this thing. Before we do this in place merge, we need to do the counting of pairs such that num I is greater than num j, right? We just need to do this. So how are we gonna do this? We are gonna as I described, we're gonna just have two elements. So we have two iterators. We iter I, it starts from the left side of the array. We iter, it starts from j, which starts from the middle of the array, like of the vector, of the vector. And then for I, I'm not abusing the I notation right now. For I equals L, I is a iterator. Remember that. For I equals L, I greater than M, I plus plus. Proper spacing is key for good programs, right? I greater than M, and for this, what you do is, while you have to increment j, while j is, r is greater than j, and num, like, there is nothing like nums of I. So how do we access what is at I? So you just do I, so dereference I of 0 is greater than what is there in j. So because we are not passing this, we're passing the iterator, we cannot have nums of I, because we know this function does not know what nums is, right? So this is where you can use, so where whatever value of I is it, we are going to that address, and we are looking at the first element of it, and we are looking at the first element of it until this is bigger, because it's an and, we'll have more parentheses. Until this is bigger, just okay, yeah, until this is bigger, just increment the value of j, right? Increment the value of j. While this is bigger, increment the value of j. And uh, after this happens, after your incremented the value of j, the value of the count of where, of the count of what I you are at. So I of 1, right? Why I of 1, dereferencing I of 1? Because uh, at position 0 we have nums, but at position 1 we have the index. So and the count position of index of where my iterator is, we have to say plus equals to, because we needed to add of them, plus equals j minus m, right? Because wherever j is minus the midpoint, so two numbers, three numbers, four numbers, that actually. So this goes from L goes from L to M, I goes from L to M, J goes from M to R, M to R, like M to R. And once we have this array, we just do in place merge, and we are expected to get the answer, right? Finally, and finally, once we do the in place merge, we are free to return, right? So in fact, you might also not return after this, because in fact we cannot return after this, because we are actually doing this. This is the return condition, this is the base condition. We don't need to return after this. So this will be like in place merge, and the in place merge will actually do the merge step. So we are actually breaking the array. When we are, it'll break until there is this just one element, then it'll go back. So until then there will be doing in place merging. Before we do the merging, we in the last we have two arrays. Before we merge them, we count the number of elements which are going to go from left to right. We don't make them go left to right, we just count how many numbers, and then it in place merge function automatically takes care of it from getting left to right. And this is how you get the answer. Let's run the code and see whether it's right or not. Could be a silly mistake, comma mistake, but okay. Where did this happen? Yeah, so basically when we are using iterators, it is very important for us to know what we are doing and what we are not doing. So there are these these errors which are absolutely not helpful, so we need to go back and see, right? Line 282, there is no line 828 at all, right? So yeah, let's now properly look at this code and debug this code. The essential part of this code is actually I've made a mistake, on my own, very knowingly. So now you have to literally identify that mistake. If you can, let me go through the code back. Uh, See where the mistake is. And So if you don't want, I'll give you 5 seconds, but if you want to pause the video, you can pause the video and see where the mistake is and tell me why this error has happened, right? Yes, so 5 seconds, if you would have paused it, you would have realized there are like two important mistakes which I did. One of them was this one, which everybody needs to know, that nums I passed as a curly bracket might not be included as a vector int, so you have to typecast it to vector int. The other crucial mistake which people make is while initializing a vector, nums 0 comma num size is not the right way of doing it. The right way of doing is num size. First of all, you mention the size and then you say how many elements you initialize it with, right? And the second mistake is the real crucial mistake which was deliberately made, and which was for you to see this thing, L minus R. L minus R is never there. Its R is greater than L, so it's always R minus L, right? So all of these three mistakes are very critical and crucial mistake. You can literally tell me in the comments how many mistakes did you get right, and how many of you are how many of you were able to catch it when I actually coded them, and how many of you were able to understand them. So understand these are three very critical mistakes. When you're having a complex data structure, having it properly typecasted, also initial knowing how to initialize your vectors well, and also having properly understanding the order of vectors, because there cannot be negative iterators. Right now, if I run my code, it is accepted, and now when I submit my code, it is accepted, right? 152 milliseconds, better than 25%. Of course, this could be further optimized in a lot of ways. This thing can also be passed as an iterator. There are inbuilt functions in C which could be used to do this, which you saw here. There is something called lower bound, upper bound, which could be explored. But at a very core fundamental level, I think this is the way you solve this question in Nlog n. And this is a very beautiful question where you use merge sort to do this. And in the future, I'm going to also cover a lot of questions in which there is a similar pattern. So merge sort can be used in questions which have a similar pattern, in which where the question says do like count numbers to the right. So wherever, or like if the format goes that you basically you have these two iterators over the array and you need to check count how many pairs I, so that I is greater than j, and num j and num I have some relation, right? If both of them have some relation, and if this is the case you need to handle, then actually, so basically numbers to the right of this, numbers to the left, like the right of this, then merge sort and using this count method is always doable in whatever problem you have and whatever condition we had. The condition we had was like num I greater than num 1, but there could be any fancy condition, 2 times this, then like 5 times this, whatever conditions you have, you could very easily solve this question. You could convert other harder looking problems in this problem, and you could solve this with using merge sort. There are also other fancier ways of solving this using things like segment tree, appending things them to tree. Those are more elegant solutions, but those are those require you to program a new data structure, which in production or in a lot of settings is not actually that feasible to do. So this actually does not use any other data structure than normal vectors of vectors, and still we're able to get an n log n complexity, right? So this was this problem number 315. There will be surely other problems like this in which this format will be used. I'll be coming to that, and we also be going to solve them with merge sort. Thank you.